Okay, good. So, okay, now let me just say a few things like properties of the Lie bracket and Lie algebras, okay?
So does the Lie algebra mean how the generators connect with each other?
Exactly.
Oh, okay.
The Lie algebra is the bracket, the bracket is a kind of product. And an algebra is essentially a, basically a vector space with a product defined on them.
So are these Lie algebra and Lie group independent? Like if I choose a Lie algebra, can we make infinite representation of Lie groups, or a certain set of Lie algebra has certain set of
no,
groups?
they are all connected. For a given Lie algebra, there can be more than one Lie group, but for a Lie group, there's only one Lie algebra, and we have already seen this because let me just remind you that we saw that for SO3, the Lie algebra was Ti, Tj. These were 3 by 3 antisymmetric matrices, actually Hermitian matrices in my convention, in the physicist convention, and they satisfied this Lie algebra. Whereas for SU2, we got 2 by 2 Pauli, 2 by 2 matrices related to the Pauli matrices by a factor of half, and they gave us the same Lie algebra. Okay, so, but as groups, they are different, right? As Lie groups, they're different. Of course, the fact that one is a double cover of the other and there exists a homomorphism between them is the reason why there is a Lie algebra. Their Lie algebra is the same, but the same Lie algebra can lead to more than one group. But given a Lie group, we have only one Lie algebra.
Okay, sir. Last question. Could you please explain that? What do you mean by antisymmetric Ti?
Right. So basically, antisymmetric T. This one.
Yes, sir. You mentioned antisymmetric. They are antisymmetric.
Yeah. So yeah, this is something we've done. Is that if we have R, a matrix which is an element of SO3, then R transpose R is 1. And if I represent R as an exponential of I times A dot T, then I just take alpha to be small, although you don't have to. But then we have A plus I this dot T, right? Now, if I put this expression in this equation, then we get that Ti transpose is minus Ti. Okay. So this condition at the level of the generator becomes the condition of antisymmetry.
So R matrix is a representation of SO3, and e to the power I alpha t is another representation of SO3.
R matrix is the defining representation of SO3. And the T matrix is the Lie algebra of SO3, is in the Lie algebra of SO3.
So both are matrices.
Yeah. You cannot exponentiate a matrix and not get a matrix. And if you have the left-hand side and the right-hand side of an equation, they both have to be matrices, right?
Okay, sir, got it. Everything is clear now.
Okay, very good. All right, so let me tell you the properties of Lie algebra and Lie brackets. Okay. Now consider, the set of generators of a Lie algebra, which I'm going to denote by G tilde. Okay, so this is the Lie algebra, and which corresponds to of the Lie group big G. So when you read mathematics textbooks, what they do is that if they have, say, a Lie group, for the Lie algebra, they use like a Gothic font. But since I'm in handwriting, it's hard for me to write a Gothic font. I will write G tilde. In context, it should be clear whether I mean a Lie algebra or an element of Lie algebra. So essentially, for example, if I'm dealing with the group SU2, then G tilde is going to be small SU2 tilde, okay? So anyway, this is just parenthetical. So let's consider the set of generators of a Lie algebra G tilde of the Lie group G. This set is linearly independent and we can add to it, say, the zero element to make a vector space, say, over the reals. Okay, it's important, whether we are using real or not. If we consider it, anyway, we'll come to that later. So now we can define a skew symmetric. So skew symmetric is mathematician's term for antisymmetric. A skew symmetric product so on this vector space. So it's a product which takes you from the vector space times itself to the vector space, right? So such that x of y is minus y of x, right? For all x and y in G tilde. Okay. So this bracket is known as a Lie bracket. If known as the Lie bracket, if in addition it also satisfies the Jacobi identity. So meaning that if I have x and y and z elements of the Lie algebra, then the Lie bracket between x and y, sorry, the Lie bracket between y and z. So, before I give you the Jacobi identity, let's just note something. It's actually a product which is not an associative product, okay? And therefore, we have to specify how the associativity works. So what is the Jacobi identity? It says that the commutator, the Lie bracket of y and z, which is of course an element of the Lie algebra, if I take the Lie bracket of that with x, and I keep doing this in a cyclic manner, then we get 0. This is the Jacobi identity. So if the generators satisfy, have an antisymmetric. Sorry, I should write the skew over here because skew symmetric. Have a skew symmetric product such that that product satisfies this identity, then we call G tilde a Lie algebra. Okay, before that it's just some set. And you can verify that because what we did over here, we derived here. This is a commutator, right? You can verify that the commutator is a Lie bracket. That is, if you take commutators of 3 elements, that they will satisfy the Jacobi identity, okay? So if you break this up into commutator, so if you treat this as a commutator, then this is going to be satisfied. So what we are calling the Lie algebra is really the Lie algebra. Okay, I think probably it's a good time to take a break. So shall we meet back here at 6:30?
Yes, sir.
Okay, welcome back. Shall I start? Okay.
I'm here.
All right, so before we left, we talked about what it means for an algebra to be Lie algebra. Okay, so an algebra is essentially it's a vector space with some product defined on it, right? So let that vector space be G, and for Lie algebra, that product is, so for Lie algebra, that product is some skew symmetric product. That means that, we take 2 elements of the Lie algebra and it gives a new element of Lie algebra, but in a way such that, if we exchange these 2 guys, we get a minus sign. So that is what skew symmetry means. And also this skew symmetric product must satisfy the certain, condition called the Jacobi identity. Okay, if these conditions are met, then we call that algebra a Lie algebra. Okay, and it's for a matrix group, we see that the commutator of 2 generators, give me another generator, right? So this is the left-hand side is a matrix multiplication. The addition of these is this thing, right? So now if I take this and so I can use this to expand the left-hand side of this, you will see that it is satisfied. Okay. But it also puts, if you now use in this Lie algebra this condition, we actually find a certain constraint on these Fs. And that's something we will, which gives us a natural representation of a Lie algebra called the adjoint representation. And when we discuss representation theory, we will discuss that. Okay, so I wanted to give you, before I give you another example, are there any questions?
This Lie algebra, does this have some sort of like a structure? Like I cannot randomly choose some generators and they cannot make a Lie algebra, right? Like they have to be a set of something, like one less member would not make a Lie algebra.
It might make a different Lie algebra, but yeah. Yeah, there could be. So if there's a Lie sub algebra, so suppose, and we'll see that if there's a sub algebra, that sub algebra closes, meaning that under the Lie bracket, you don't go outside that subset. Then that sub algebra will generate a subgroup of the bigger Lie group.
And if
Okay.
yes, sir, if I add a new element in the Lie algebra, that has to match with the Lie algebra, or it won't.
Yeah. I mean, if you add a new element and it expands the Lie algebra, then of course you're going to have a new Lie algebra and a new Lie group, right? So it is the converse of what I just said before. So yeah, we'll come to those examples. You'll see examples of all of that.
Yes, sir, got it.